today, but thank you. Thank you for remembering. Um, um, Usually there's more than one officer present at these, but uh, people have other obligations, unfortunately, today. So I'm the secretary. Chris Bennett is the chair this year. Michelle Nuevo is the chair-elect. Our newest officer is Jamie Elsala, who is the vice chair this year. And Kyle Crabtree is our past chair. I have a couple of quick announcements and then we'll gear up for the AstroCheminar itself. We are offering the dissertation prize this year, the outstanding dissertation prize. We're waiting on word from ACS about a particular detail before we issue the nomination. Basically, we need to know how much prize money we're going to be able to offer this year. I think we're quite likely to change the deadline from January 31st to probably sometime in February or even later, because it's getting pretty close to the end of January already. I will be sending out a newsletter soon with more information about that and a couple other things that people have sent me to pass on to people. All right, so this year we are doing things a little bit differently with the AstroCheminars. We're sponsoring two different types of events. We're doing webinars that are co-sponsored with ACS. We did one in November where Adina Van Dishuk talked about JWST results. And we are going to be doing one in April where Pepe Cernacharo will speak. But the other seminars we're turning over to be run by grad students. And as you can see, the two grad students, Catherine Walker and Kate Gold, are here today. I'll be passing things off to them in a moment here. And they're going to talk a little bit about what they're doing with their seminars, and then they'll introduce our speaker, Coco Zhang. Here you go.
Thanks, Dave. Yeah, so what we're really excited about and interested in when we're organizing these seminars is trying to really connect the astrochemistry community and especially uplift graduate students and early career professionals and kind of connect them to other people in astrochemistry. So we really want to showcase the diversity of astrochemistry research, support graduate students and provide this platform for people to connect with each other. So we're hoping by having these be more, by having those goals in mind, these talks can help people connect, and as well as we're interested in having more graduate students talk as well. So if you or somebody you know is interested in giving a talk at an AstroCheminar, and that could be a short talk or a long talk, please have them reach out to myself and Kate directly. Our emails are on the website, which we'll be putting in chat at some point. But yeah, so my name is Catherine. I guess maybe I should have started with introducing myself, but I'm a third-year graduate student at the University of Wisconsin-Madison. I study under Professor Susanna Whitkus-Weaver, and I'm really interested in thinking about how chemicals are formed in the interstellar medium, how chemistry happens at a molecular level, especially on icy dust grains. Kate.
Yeah, thanks, Catherine. Yeah, we're really excited about these graduate student-led AstroCheminar events. We do want to focus on research and also focus on community. And so if you're interested, as Catherine said, in helping with one of these events, either in organizing or as being a speaker, do reach out to us. We will have events that are graduate student focused. And so whether you're a graduate student or a postdoc or more established, do reach out to us. We'd love to have you assist on the team as a speaker or an organizer. And so, yeah, and so I'm Kate Gold, and I'm a graduate student in chemistry at the University of Arizona. I study under Lucy Zuris. I do mostly observational astrochemistry, studying evolved stars. So my work is on planetary nebula, protoplanetary nebula, and understanding not only chemical evolution, but also kind of molecular recycling, if you will. And so that's really exciting work, and I enjoy it a lot. I'm also excited to lead our event. Today we have Kay Zhang from the University of Wisconsin. And so we're excited to introduce her and also for her to join us, as well as you guys as our audience. So thank you all for coming today.
Yes, so we're very excited to hear from Professor Zhang today. Professor Coco Zhang received her BS and MS in the field of astrophysics from Beijing Normal University in 2005 and 2008, respectively. She then completed her PhD at the California Institute of Technology under her advisor, Jeffrey Blake, studying volatiles in protoplanetary disks. After this, she worked as a postdoctoral researcher and a NASA Hubble Fellow at the University of Michigan from 2015 to 2020. She is currently an assistant professor at the University of Wisconsin-Madison in the Department of Astronomy. Her team has been awarded observational time on the ALMA, JWST, NOAMA, PARMA, and IRAM 30-meter telescopes. So I hope you all and I myself are very excited to hear about some of that work with Coco's talk, which is titled Decoding Mass Evolution in Planet-Forming Disks. So please take it away, Coco.
Yeah, thanks, Catherine and Kate, for inviting me. I'm pretty excited for the opportunity to talk about our recent approach using astrochemistry approach to study planet formation. Is the slide look okay? Okay, assure me it's okay. Yeah, so this is a question we mainly want to see how astrochemistry can help us understand some fundamental properties and process in planet formation. So a little bit motivation here. So one of our ultimate goal in astrochemistry and astronomy in general is trying to understand the formation of habitable world and how we can find another habitable world beyond our solar system. So there are three angles we can use. One is our home solar system. So we can study our planets in exotic details. And now with more than 5,000 exoplanets, we can also study other planetary systems, not as much detail as our solar system planets, but we have a lot more numbers and we can study their populations. And finally, we can look at where things are happening, where the building process of planet formation are happening in the nearby star-forming regions. So we can study those planet-forming disks to look at the very initial beginning and how the things are and what steps happens during planet formation. So with those three approaches, we all working towards the angle, trying to understand the building process of habitability. So today's talk, I'm going to focus on our study on protoplanetary disks, just to bring everyone into the same picture. So when we talk about protoplanetary disk, what we are referring to. So planet formation is a natural byproduct of star formation. It all started in the colder, denser part of molecular cloud. It started to collapse and form a protostellar core. But due to angular momentum conservation, all of the materials cannot directly fall into the central star. It has to form an accretion disk, which regulates the angular momentum. So that is the accretion disk is generally the starting of a protoplanetary disk. At the beginning, there may be still many materials falling onto the central star, and there can be energetic outflows. But after about 1 million years, most of the envelope material is gone. So now we have a pre-main sequence star and accretion disk. So this accretion disk can be a few hundred AU sizes. So this accretion disk stage is what we refer as protoplanetary disk. They are gas-rich disks around young stars. So for simplicity of this talk, I generally refer those two stages both as protoplanetary disk. So this stage can last for a few million years. It's pretty short compared to the whole lifetime of a star, but it's in this short stage, many of the fundamental steps of planet formation happens, and fundamental properties of planetary system are set at this stage. So at this stage, micron-sized interstellar medium particles need to grow pebble sizes to kilometer-sized planetesimals and eventually to planetary cores. And also, if we want to have any gas giants in the system, it has to form inside the protoplanetary stage because it has to accrete those hydrogen-rich gases. So that's the focus. We want to understand this stage, see what's happening. And one of the most fundamental property for protoplanet disk is its mass, especially the gas mass, because we know for initially 99% of the mass should be in the gas, and mostly in molecular hydrogen. And to know the amount of gas inside those disks and how are they distributed, it's always a fundamental input for our planet formation models. So gas regulates the dust dynamics, how the dust particles grow to pebbles, planetary cores. They're all regulated by their interaction with gas. And also to form any planets with hydrogen-rich atmosphere, whether sub-Neptunes, ice giants, gas giants, it depends on how much gas available during their formation stage. So this gas reservoir is what we need to know in order to understand what type of planets can form. And finally, when planets form, they also interact with their gas disk, so they can migrate inside the disk and moving away from their birth location. So which direction they move and how fast they migrate all depends on the amount of the gas, how it distributed inside the disk. So it's very fundamental for us to know how much available and how it's distributed. So the classic reference to understand the amount of mass in protoplanet disk is the minimum mass solar nebula. Usually see the MMSN. So this picture is showing you, it's a very simple idea. So we have our planets in the solar system. If you take the mass of those planets and assume the solar composition to see how much amount of mass need to be there initially in order to recover the whole solar system. So you do this mass, you will find roughly you need 1% of the sun's mass in order to rebuild our solar system. So you may need more, but this is the minimum amount in the classic picture, how much we need to build a solar system. But we don't know whether this is typical for other planetary systems and what's the process. So that goes to our study of protoplanet disk. We want to measure those disks, see what's their mass, and how whether their mass start to evolve over time. So there are plenty of evidence showing protoplanet disk is not a static structure. It evolves over the few million year lifetime scale. So the first evidence comes into the earlier 90s and the 2000s. So the idea is if you can measure the photometry, the total brightness of the system at different wavelengths. So very wide range of wavelengths from optical to millimeter wavelengths. What you will see, it looks like this shape. And in the optical region, that's the photosphere of the star. But you will see when you move to near IR and longer wavelengths, you have much higher flux compared to what you expect from the photosphere of the star. So that's called the near IR axis. So you can come, that's the indication of you have a dusty disk around the very young star. So we can do counting of the young stars, which shows those IR axes. And very interestingly, you will find for stars, so those are based on the star forming region ages. So the fraction of stars with those axes generally decrease over time at a time scale about 3 million years. So that's the first indication about the gas amount in those disks they evolve. And later, over the past decade, there are more evidence showing the evolution of protoplanet disk. So now with sensitive millimeter observations, we can measure millimeter continuum flux of those disks at different star forming regions. And what you can see here is how the amount of dust mass traced by millimeter flux changes over time. So those are ages of different star forming regions. And for younger star forming regions within 3 million years, you see they're pretty similar. But once you go to 5 to 10 million year regions, you see 1 order of magnitude decrease in the dust mass. So this is another evidence showing prime photophore disk, they evolve over time. But all of those evidence, they don't directly trace the dominant amount of mass, the gas mass. So they are kind of indirect tracers showing they are involved, but we don't know how much mass they have and how the amount change over time. So there are 2 leading theories about the evolution of photophore disk. Both focus on understanding the transport or removal of angular momentum in the disk, because that's how materials get accreted to the center star. They have to lose their angular momentum. So the first leading theory is there is turbulence in the disk that produces a viscosity. So most of the amount of the mass, they lose their angular momentum and transport the angular momentum to small amount of mass. They spread out, while the most of the mass, they lose angular momentum and get accreted into the center star. Another idea, which is getting more popular over the past decade, is it's called the MHD wind. So this idea removes angular momentum from the disk. So instead of redistribute the angular momentum, so some materials escape from the disk along with the magnetic field line, and they carry angular momentum away. So in that way, the rest of the material lose angular momentum and fall into the central star. So, but we don't know if either of those mechanisms is correct or which one is dominant. So over the past decade, there has been tremendous effort trying to understand how the disk evolves and which mechanism may be correct. So there are 2 approaches to study those. One approach is we can study individual disks, trying to identify the effect of those mechanisms. For example, trying to measure the turbulence and to observe those wind. But in general, it has been very difficult to have direct tracer of those effects. Another one, which we'll more focus on this talk today, is trying to study photophore disk as a population, trying to study, say, given a certain age, how the average disk mass look like, whether there is an evolution over time. So as you have seen in the dust picture, we have known the average amount of the dust mass seems to decrease over time. But we don't know for the gas whether it gives us the same picture or it's a different type of picture. And if we were able to do that, we can test the evolutionary theory. So for this one, it shows for 2 types of theoretical prediction how the gas disk mass would change over time. So don't worry about those small marks. Look at the red and black lines. So the idea is basically showing you if we can measure the gas disk mass, the 2 mechanisms will predict very different evolutionary patterns at different ages. So for example, the wind cases, the gas mass will drop much quickly. And also we can observe gas disk sizes. In the viscous case, the disk will spread out, while in the wind case, in general, the apparent disk size will shrink over time. So the idea is if we can observe the gas mass to some accuracy, we should be able to test those 2 leading theories. So that comes to the question how we can measure gas disk mass. When we talk about mass, the first impression is Newton's law, right? So that's how it's defined. So people have tried to use a dynamic approach to measure it. but the disk is like 1% of the stellar mass, so it's a minor effect. So it's very hard to directly measure the disk mass from the dynamic approach. So usually we try the other approach. We use radiation. So one popular way in the past is to measure the dust mass from continuum and do a correction of the gas to dust mass. But this correction becomes highly uncertain over time. So it's not a good tracer to trace gas itself. Instead, a better way to study gas mass would be we use gas tracers directly. Unfortunately, most of the gas is in molecular hydrogen, which doesn't have a permanent dipole moment, and therefore no strong lines at the 100 to 20 Kelvin low temperature region. So we usually use some other molecules to trace the H2 mass. So the best tracer will be deuterated version of H2, but that requires far infrared telescope, and we currently don't have one yet. For other molecular tracers, typically like carbon monoxide, but that would require our understanding about the chemical structure in the disk. So that's where our understanding of astrochemistry comes to the rescue to say how we can use other molecular tracers to constrain fundamental property of planet formation. So when you look at CO, you see this is the most common molecule we use in the interstellar medium molecular cloud. We should have a pretty good understanding of it, right? Yeah, so in molecular cloud, we know the CO to H2 conversion factor is about 10 to minus 4, and that's well tested. And how about we just use a two-protoplanetary disk, right? So it seems disk form out of a molecular cloud. Well, that's what the people thought we could do. But after the past decade, more and more evidence showing the CO to H2 abundance in protoplanetary disk, it's not as simple as we thought. So this is showing you the CO abundance, how it changes over time, seeing different star forming region and individual disks. So for the very young disks, less than 1 million year, you can see the CO abundance seems to be, as expected, consistent with the interstellar medium value. But as time goes by, seems there is wide diversity of CO abundance, 2 orders of magnitude possible values. And also it seems it changes over time. So that makes a big question mark if you just use CO to measure the gas mass. And so we now know it's not a robust gas mass tracer, but how can we do this, right? So this is the part our knowledge about astrochemistry, yes, comes to the rescue. So you can think about, we think CO is not a good tracer because its CO to H2 abundance ratio can be a large uncertainty. What if we can have another molecule, or ion, it's an indicator of the CO to H2 abundance? So yeah, so that simple idea is the approach we're trying to use here. So this one, we choose N2H+, and N2H+ is an interesting ion. Because its formation and destruction, it's highly related to the gas phase CO. So first of all, when the gas phase CO is around, N2H+ can easily be destroyed through this reaction. So it forms HCO+ and molecular hydrogen. So N2H+ is destroyed. And the formation of N2H+, it's also related to the CO gas phase abundance. So the formation of N2H+ requires N2 to react with H3+. But CO also react with HCO+. So there is a competition between N2 and CO to use H3+. So N2H+ formation and only being abundant when the CO gas abundance is low. And also when the gas CO abundance is low, it can survive. So it has this nice correlation. NH plus high need to have low CO abundance. So this is showing you if we measure the NH plus to some optically thin tracer of CO, say C18O, it's tracing more the column density of CO. So this ratio actually have a pretty good correlation with the CO abundance in the gas. So with high CO abundance, the NH plus to CO ratio is low because NH plus is hard to form and easily destroyed. And when the CO abundance is low, we have more NH plus in the gas. So this has been benchmarked. We did the test before we applied to more propane disks. So we did the benchmark test for 3 propane disks. We chose those 3 because those 3 has independent gas mass measurement from HD. So the only 3 disks which has HD measurements. So what you are seeing here, the bottom is the C18O flux, and the y-axis is the gas disk mass. So 3 columns here are 3 disks. So you see the colored dots here? That's if we just take the C18O flux and convert it to the amount of gas. We have a 2-order magnitude uncertainty. So this shows the whole range of possible gas mass because the CO has 2 orders of magnitude uncertainty in the abundance. But if we add the NH plus information, now we narrow the possible CO abundance because of NH plus to C18O ratio. So the orange box showing the parameter is tremendously narrowed down. So in some case, 1 order magnitude, other case even by like 50, factor of 50. So now you see this is the gas mass range. Now you combine NH plus and the C18O. And we compare this with the gray area, which is a possible range based on HD measurement. So in general, this shows good agreement with the HD measurement. So with this method, it unlocks a new pathway to measure gas disk masses in a large population of disk. So we don't need to wait for the next far infrared telescope. We don't know how long it's going to be. But now we can do it on the ground with AMA observations. So we can do hundreds of disks. So with those measurements, we should be able to test the fundamental theories about how propane disk evolves and how quickly the gas mass decreases. So that's the basic idea, the foundation of this idea. So we take this idea, we proposed for Armatan and get awarded a large program, about 100 hours to do this. So the program is called the ARMA Survey of Gas Evolution in Propane Disk. The nickname is HPRO. So our goal is with this program, we want to systematically trace the evolution of gas disk masses and sizes over the lifetime of propane disk. Basically trying to have a picture about how those disk masses change over time and what we should use for plant formation models. So if you are not familiar with AMA, so AMA is the Atacama Large Millimeter Submillimeter Array. It works at the millimeter wavelengths. The main array has 50 antennas. Each antenna is 12 meters diameter each. You can 6 people lined up. And the resolution give us superb resolution to look at details in the nearby propane disk. So we can look at those disks at a resolution about a few to 20 AU resolution. And it has the unprecedented sensitivity for us to study a wide range of molecules. So with this ARMA, so we have formed our team, HPRO team. What I'm showing the result today here is a huge effort from everyone in the team, especially our graduate students and postdocs So we are really did the heavy lifting works. So to do this program, we're trying to minimize the other effect rather than focus on the evolutionary effect. So what we did is we chose 30 disks to cover the whole gas disk lifetime. So from 0.1 to 10 million year. And we focus on 3 star-forming regions to sample different ages. So Ophiuchus region, the roughly less than 1 million year, and the lupus region 1 to 3 million year, and upper school region to sample it the oldest region. So our selection criteria is we try to narrow down the stellar effect as much as possible. So we have a pretty narrow stellar mass range, roughly from 0.3 to 0.8 solar mass. And we're trying to choose sources close to the region's medium age. And you can see in the HR diagram here, so those black lines showing you the theoretical evolutionary tracks of pre-main sequence stars. And Ophiuchus region sources are in this region, generally less than 1 million year. And lupus region trace 1 to 3 million year, and upper skull trace 5 to 10 million year sources. And as we mentioned before, it's known the gas disk mass in different ages generally decrease over time. So as you can see on the right part, so this is showing you the millimeter luminosity of those sources represent the dust disk mass. So they generally follows, you can see the median value clearly decrease over time here. So with this sample, it's still like a rather small sample because line observations are expensive. But with this first population study, we want to constrain the gas mass directly. So the setup is for the youngest region, Ophiuchus region, the CO abundance is still expected to be interstellar medium. So we use 4 CO isotope logs to probe different optical depths to measure the CO gas mass and then the total gas mass. Well, for the 2 older region after 1 million year, we know the CO abundance can have a wide variety of abundance. So we add the N2H plus to calibrate the CO abundance and use CO plus, N2H plus to combine gas mass together. So this is showing you an example of one of our sources, example molecular lines we detect. So this source is one of the intermediate age one, the lupus source. So you can see the continuous emission at 1.3 millimeter and the CU isotope log lines and N2H plus. And we also detect other molecular lines, can see it at the bottom. But the key signs, the gas mass and the size are from the first rows. So the 12 CO line gives us the size of the gas disk, and the isotope logs plus N2H plus will be used to constrain the total amount of gas in those disks. So this is showing you the mosaic view of Ophiuchus region. So this is, we're trying to finalize those images, so those are still preliminary, but you can see how the data really look like for the whole star forming region. You can see here, this is 1.3 millimeter continuum, tracing the thermal emission from millimeter size dust particle. They look pretty regular and compact. The 12 CO looks pretty irregular. It's mostly because at this very young region, there are still envelope materials falling onto the disk. So we are seeing both the disk and the cloud. And when you go to C17O, it looks cleaner and mostly tracing the disk regions. So the colored ones are robust detections, and the gray ones is we don't see clear detections. And when you move to older region, so the intermediate age lupus, and you can see the 12 CO looks much cleaner than the younger region. So 12 CO compact, rather compact disk. One thing is, we were expecting to detect N2+ for most of the lupus disks, but instead we only formally detected in 3 sources. So this is comes as a little surprise, but we'll talk about more in the next few slides. And then our oldest region, upper skull region. So this is sampling 5 to 10 million year old regions. We have beautiful view of CO isotope logs, and about half of them we detect N2H+. So this is just a quick view about the line flux. So you don't need to pay too much attention, but I want to highlight here is, so the 2 colors, lupus and upper skull. So the y-axis is their line flux. So one surprise things we find is in our sample, the 2 regions in terms of the different molecular line flux, they seems to cover a pretty similar region, so which is rather unexpected, because we would think the upper skull regions is much older, it will have much less gas and fainter molecular lines, but it seems it's not the case. So how are we considering the gas mass? So this is the procedure we are doing here. So this is the work led by my postdoc Leon Chapman, and we'll finalize the paper, want to submit within maybe earlier March. So this is, we use the molecular lines, CU isotope blocks and N2H+. So we take those line fluxes and compare with a huge grid of thermochemical model of protovan disk. So this grid cover a wide range of the gas disk mass, CO abundance, disk sizes. So we compare our observations with this large grid to calculate the posterior probability distribution of the parameters we care about. So there are a bunch of parameters, but the most important is the gas disk mass. So that's the fundamental property we want to get. So this is an example of the posterior distribution thing. For this disk, it's about -10 to -3 solar mass. So this is the final result, and this is preliminary, so please keep it confidential. So this is showing in our sample. Different color represent different star forming regions. So the youngest of fucus, intermediate lupus, and the oldest upper skull. So showing their dust mass and gas mass distribution. So remind about the reference value for our solar system, the minimum mass solar nebula is here, about 1% of the sun's mass, and Jupiter is about 0.1% of the sun's mass. And as you can see, the 3 star forming regions, there are some interesting things here. The one is the youngest region of fucus, clearly has the highest gas mass. This is showing you the median value here. But the lupus and upper skull regions, their median mass seems to be rather similar, right? So you see this offset here. Another interesting thing you can see here is our Jupiter mass. You will see for our sample, it seems once they evolve to the lupus and upper skull age, it seems the majority, the average disk don't have enough mass to form a Jupiter. So that's a very small amount of gas mass. Okay. So yeah, so this is just a posterior probability distribution for the median gas disk mass in the lupus and upper skull region. So this is just to show you, within the uncertainty, those 2 regions, even upper skull, it's much older, it seems to have very similar gas mass. And this is not what we expect to see. This is go back again for the theoretical predictions, is we will see a very quick drop of the gas mass to the older disks. And not as quick, but still drop in the gas mass in the viscous cases. But this our points does not tell either of the story. So we are still working on this, trying to say how our results can be interpolated in either of the theory and what does tell us. But back to again to average disk mass is our solar system. We said the minimum amount we seems to require 1% of the solar mass. But in the medium disk mass from 1 to 10 million year old disks around, so our sample is mostly focused on lower mass, slightly lower mass stars. It's more like 0.1% of the stellar mass. So much less than our solar system, the expected minimum value. And this is the gas to dust mass ratio in the sample. And as starting, the youngest region is about 100, very similar to interstellar medium. But interesting things is in the intermediate age, lupus region seems to have a pretty low gas to dust mass ratio around 10-ish. But when we evolve to the older disk, the upper skull region, they have a gas to dust mass ratio higher again. So this is mostly because the upper skull region, they have much lower dust mass. And even they have the similar gas mass with lupus, but because of their very low dust mass, they have a pretty high gas to dust ratio. So if we're planning from at lupus compared to upper skull regions, so the gas to dust amount mass they could accrete will also be very different. Okay, so finally, it's a CU abundance. So since we have both NH plus and the CU isotope logs, we can use the ratio to calibrate CU abundance. So what we find is generally the two regions are rather similar, and you might say even the medium upper skull region is slightly higher CU abundance with lupus. So, and again, this is not what we expect to see. We were thinking about maybe the CU abundance will decrease over time, so the upper skull regions will have lupus lower than the lupus region, but this seems to be pretty similar. So we have all the basic results. So we have measured the gas disk masses, and now we are trying to interpolate it in the theoretical models. So this is a work led by our collaborator, Benoit Talbot. So he's doing a large population synthesized model, testing both viscous disk and MH disk, wind disk, and trying to see what parameter space can match with our observation. What does this mean for planet formation, the amount of mass reservoir for planet formation? And we also wanted to try to understand the spatial distribution. That means at different distance, how much amount of gas is available for planet formation. So this is a work led by my graduate student, Stephanie. So she's working on this, trying to say the CU column density distribution and how it changes at different radius. And finally, since we have both gas and dust measurement, so we have collaborators working on involve the dust and the gas simultaneously to say how our observation of the gas disk size compared to the dust disk size to constrain those co-evolution models. I think this will be very useful information about generally like the pebble draft inside disk and how pebble growth changes over time. So for the first batch of papers, we are expecting 7 key papers to be published earlier this year. So we have the statistics from different star forming regions and the gas mass, and the 2 theoretical papers compare our results with disk population synthesis model and the co-evolution of the gas to dust disk. And finally, we will have an overview paper to talk about the program setup and the general statistics. And there is, based on the same sample, there are upcoming JWST observations to study the same 30 disks. And the JWST infrared spectrum will reveal water and small organics in the inner 1 AU regions of those disks. And with those data, we're trying to understand two fundamental things. One is how the volatile budget in the gas of the terrestrial planet forming region changes over the disk lifetime, and how the any pebbles drift from the outer region AMA sensitive to the inner terrestrial regions. They can bring water and other volatiles to the inner region. So how those pebble growth and drift will change the volatile composition available for terrestrial planet forming regions. So most of our JWST observation will come in the spring and in the summer. So, and hopefully in a year, we will have new results to present you saying, what does this tell us about the budget, water and the small organic budget available in the terrestrial forming regions. So this is final part. I would just wanted to have like a quick thing about the pebble drift. So the pebble drift idea is a popular idea in planet formation now. It's saying once solids grow to some critical size, say centimeter sizes, so they are no longer space dynamically coupled with gas, so they can move into the inner region much faster compared to the gas. And because they have ice on top of them, so they can they can move into the warmer region of the disk. And for example, for the CO ice, once they cross the CO snow line, so they can evaporize and bring volatiles back to the gas phase. So this is a way to transport volatiles from different disk regions to the terrestrial regions. So there are already preliminary evidence. One is from AMA showing there are some disks inside their CO snow line. Their CO abundance can be superstellar, which indicate a superstellar C/H ratio. More recently, I'm on a paper published by our collaborator Andrea Benzatti, showing exact same thing we are seeing in the JWST spectrum. So there are two types of disk. So he observed. So one is a compact disk, which doesn't have much substructure in the continuous emission in sub-millimeter. Another type is much larger. And the mirror spectra, infrared JWST spectra of the two types show a clear difference. And the more compact disk show actual water emission, cold water emissions. So you can see the difference. So the white line is extended disk, and the blue line is compact disk. And those compact disks have those extra components from the cold water, which are consistent with the pictures. Icy pebble brings extra water, because those small disks, more pebble has drifted in. So bring waters to the terrestrial region. So for the next coming year, I expect there will be many exciting discoveries about more this type of effect. Help us to understand the budget for terrestrial forming. So finally, this is my last slide of summary. So we are doing the first systematic study to trace gas evolution in protoplanet disk. One biggest surprise is we find the oldest disk in our sample seems to have a comparable disk mass with the intermediate age, which is rather unexpected. And finally, in the coming years, the synergy between AMA and the JWST will help us understand more about the gas evolution in disk, especially the volatile budget. That's all. Thanks.
Thank you, Coco, for that very fascinating talk. We're gonna move right into Q&A, I think. So so we've already had some questions put in the Q&A box. if you have a question for Coco, you can type it in the box and Kate and I will read it out. Or if you would rather ask your question, like speak it, then type it, we can, you can, I think you should be able to raise your hand. And Kate or I will unmute you. And so one of the questions we got was from Daniela, Isabella Avia, and Davide Bigatti, who asked, could you explain why it is gas that regulates dust dynamics?
So it's basically because initially the gas has a much higher mass compared to the dust particles. So you can think about a small dust floating in the air. So it's the dynamic interaction between the gas and dust regulates the formation of larger dust particles and eventually to kilometer size planetesimals and planetary cores.
Great.
Thanks for that answer. There was another question asking about the polycyclic aromatic hydrocarbons and how that accounts for the gas dust and kind of which of those hydrocarbons are the most abundant or the ones that are most connected in that way.
Yeah, so when we say hydrocarbons, there are so many different levels, right? So for protoperiodic disk observations, C2H seems to be pretty abundant, especially in the older age, say a few million old disks. There is upcoming AMA large program specifically study simple hydrocarbons. But for more complex ones like the PAS, and so infrared observations, they mostly detected in the more massive sources, say 2 or 3 solar mass stars in their infrared spectra. But for the sun-like stars, there are very few detections of PH emission features. So people think they may because the they made the temperature is not enough for us to see the emission feature, but they still exist. And whether they count as dust and gas, that's a question under debate. But in general, they have very small amount of mass and they don't count much for the total gas budget.
Thank you. Another question that came in was from Philemon. I think this came out when you were showing the array of images. So they ask, does the sun's radiation account for the altering of the results of the gas dust as far as the gas detection is concerned? So I think maybe they're wondering if the protostar, if that radiation impacts the way that the dust is detected.
Oh, I see. So, my understanding is, so if the disk is warmer, then it does have more thermal emission and it's easier to observe. But for once we have the fluxes, we convert to the gas mass, already taking into the stellar luminosity into consideration. So that's already factored in the large thermochemical grade. We also vary the stellar luminosity by a large range.
Thank you.
Great.
It looks like Simon Tong added a comment as well. He writes, "Hi Coco, thank you so much for the great talk. I really enjoyed it. I have a naive question about constraining the two scenarios by disk size. It seems that in the initial disk, sizes are assumed to be different for two mechanisms, as inferred by the picture. Is that something we also assume in our research?"
Yeah, so for this particular model is we're trying to have the model match with the medium size measured in this 1 to 3 million lupus region. So that's why the model is usually anchored in this region. So this one is the uncertainty is before our H Pro observation. So this large error bar is from previous shallow survey That's how we prepared this figure thing. But now with our observation, we are narrowed down the error bars, but we're still working on it. And we have 3 data points instead of just 1 data point. So we have the Ophiuchus region, lupus, and upper skull regions. So we can better constrain the 2 models. Yeah, I hope that answers the question.
Thanks. Smith might let us know. Another question that was put into the Q&A was about the CO, and I'm not necessarily sure if this person is wondering about how CO is formed or how it gets into the dust or into the gas phase. But they ask, is the CO released by PAH molecules?
No, I think the main formation, I think most of the CO formed at the molecular cloud stage. And the total abundance of the CO is much higher than the pH. Yeah. So there may be there has been hypothesis in the later stage when the overall CO abundance is much lower than the interstellar median value, like say 10 to -6. The release of pH molecules can enhance the total amount of carbon in the gas, but that's at very late stage when CO abundance is much lower than the interstellar median value.
Is that a stage much later than the stars you looked at in the HPRO survey? Or sorry, the
It could be
disks?
at this 5 to 10 million year stage. So there has been one 10 million year old protoplanet disk TW Haya, which has a very strong hydrocarbon emission. And the hypothesis is why it's so particularly strong. Maybe the gas phase, the overall elemental ratio is over than 1. And the actual carbon is from the release of pars. But yeah, so that's like one hypothesis.
Thank you.
Yeah, we've exhausted the questions in the Q&A, and so if anyone else has a question, please add that or raise your hand so that we can have your questions answered. I had a question myself, and I'm not very familiar with protoplanetary disks or carbon 17 or C18O. But I was curious about the substructure and some of the plots when you compare CO and the carbon 17O, carbon 18O. And so I'm curious about some of the substructure that are seen. I understand the difference in source size, but I'm just really curious.
Yeah, so for the Ophiuchus region, so some of the substructure you are seeing here may be from the cloud contamination rather than from the protoplanet disk itself. But there are some disks which has very clear substructure. Like you can see this one, it has a ring in the continuum and also in different type of gases. So that is saying there may be a real cavity even in the gas in this disk. And the gas is distributed in this ring and very reduced in the inner region. So people call those transitional disks. And the hypothesis, maybe there are giant planets forming inside those gaps and they are carving out gaps inside those disks. Yeah, so we have a follow-up arm observation for this particular disk and to basically search for any planetary signals.
Thank you.
And someone just asked, they say, I might have missed this, but how do you determine the age of a protoplanetary disk?
Yeah, that's a really good question because age is super difficult. So the typical way people to do it is to measure the effective temperature and the luminosity of the star and compare it with the theoretical evolutionary track of pre-main sequence stars. So like say if you measure a protoplanet disk, the system has a stellar luminosity this and the effective temperature this one. And you say compared to the theoretical age, I would say it's maybe a 0.5 solar mass star and at the age of 1 to 3 million year. It's highly uncertain when you have a different evolutionary tracks, the age can be different. But that's the best way we are doing it now. And for general, like individual stars, it's very hard to say its age. So that's why we are trying different star forming regions and uses the median age of a star forming region to represent the sample.
Thank you. The attendee has added a thank you as well in the chat.
We are getting to the end of our hour, and I want to respect everybody's time. Do we maybe want to take one more, or we can close?
It does seem like there's one more question, kind of talking about a very different part in the cycle. So instead of star formation, there's a question about evidence of gases from the destruction of stars. And that seems a little bit different than your research. I don't know if you want to comment on it. I think we might.
The destruction of star, that's after the main sequence, right? So we are trying to figure out what happened to pre-main sequence during the planet formation stage. I'm not an expert of involved star, but I think that's also a fascinating stage. And my colleague Juliet is studying the potential habitable world for the end stage of, yeah.
Well, thank you everybody for your attention, and thank you, Coco, for your for talking about your research and answering questions. It was very interesting. We are going to close then. Just wanted to remind everybody, if you're interested in more AstroCheminars, you should check out our website. It was posted in the chat box a little earlier up. You can also find Kate's contact info there and my contact info there. And if you have any further questions for Coco, you can also contact her. I believe her email will be on her website or somewhere on the UW page. I don't know. Yeah, we can make that happen. And we hope to see you all again next month for a talk by Professor Heather Abbott-Leon on February 14th. So keep an eye out for more information coming about that. I guess, Kate, do you have anything to add?
No, nothing to add. Thanks everyone for coming. The other thing that we're looking for as we build these graduate student-led events is some help sharing it. And so if you have a Twitter, do forward, if you see it on Twitter, if you see an email, forward it to your departments, put it on your Twitter feed, etc. And that'll help get us attention and help these continue on. Thank you.
Thank you, everyone.
Thank you. Is there anything else we need to do, Kate and Catherine?
I think we're all good.